Okay, so in this video we're going to calculate the homology groups of spheres. Okay, so the theorem is like this. Let's start by so let's start by describing the homology of the zero sphere, and then so that's and then for n bigger than 0, the claim is that h naught of Sn and hn of Sn are both isomorphic to the integers, and hk of Sn is 0 for k not equal to n. So I mean, you should kind of really think about these as being the case n equals 0 is not particularly special. I mean, here you've got two copies of z in dimension one in dimension 0, one in dimension n, and then here you've got the same two copies of z. It's just that n equals 0, so they both two copies of z both appear in the same place. So the proof, well, of course, for S0, this is just S0 is just 1 and just a set containing 2 points, 1 and -1, and pi 0 S0 has 2 elements, and so so the homology of S naught is given by the general rule for a finite discrete space. Right, so I mean, for S naught, of course, any continuous map from a simplex to S naught has got to be constant. And as we described earlier, because all maps are constant, it's very easy to understand what the chain complex is and what its homology is, and we just get this answer that I've written here. So now let's think about S1. So S1 is like this, of course, and we're going to do the Taurus sequence. So U is going to be like this. Actually, maybe we'll have do it the other way around. Doesn't make much difference. We'll do U is like this. So I've taken out the point at the top, and V is going to be like this, where I take out the point at the bottom. And so U intersect V is going to be so I've taken out the top and the bottom, so I just get two arcs like that. So these two spaces that we've got here, my U and my V, these are both contractible. Okay, I mean, this is just like an open interval curled around. Both of them are just like intervals curled around. Oh, I didn't write. Okay, so U is this one, V is this one. Both of those are contractible, and so they've got the same homology as a point. And then this one is that's homotopy equivalent to S naught, right? Each of these two arcs is contractible, so it's a homotopy equivalent to just a pair of points, which is S0. Okay, so we know the homology of both of U, V, and U intersect V, and we can use the Taurus sequence. Okay, so what do we have? We've got S1 is U union V. U intersect V is homotopy equivalent to S naught. U and V both contractible. Okay, so so if we look at H0 of U intersect V, so that's got it's a free abelian group on two generators, one for each of the two path components of U intersect V, and then H naught U and H naught V. Well, they're both copies of Z, and if you think about it, right? I mean, so yeah, A is a point in U intersect, or corresponds to a point in U intersect V. And so does B, and the 2 points A and B, they're not connected in U intersect V, but they are connected in U, and similarly they are connected in V. So yeah, we can think of the generator here as being A, but B is equal to A. Okay, so when we map over to U, A and B become connected, so they give you the same element in H0A, H0U, and similarly they give the same element in H0V. And when K is non-zero, because U, V, and U intersect V, they're all homotopy equivalent to just either 1 point or 2 points, so they've got no more homology. So that's all there is. So now we have so we've got a Majorvian Taurus sequence, which looks like this. So towards the end, right, you've got H naught of S1, and then you get H naught U plus H naught V, and then you get your H naught of U intersect V, and you get your H1 of S1. And then the next term is, in principle, is consists of H1U and H1V, but those are all 0. And then the next term back is, in principle, H1 of U intersect V, but that's 0 as well. And then you've got an H2 of S1, and then going back here, and some more stuff. Okay, so we'll worry about what goes on there later. Let's just think about what's happening over here. Okay, so okay, so again, S1 we know S1 is also connected. So this again is just going to be Z generated by the same element A. And then here this was Z get generated by A and B, and so you think about what happens. A goes to sort of just A comma A. This map, the definition of this map here had a minus sign in the second factor, so this goes to A comma minus A, and then here the B also goes. B becomes connected to A in either of these spaces, so it works exactly the same. You get A and minus A. Okay. And so because of this, A minus B goes to 0. Okay. So we call this map delta here. So we find that the kernel of delta, just reading off from this description here, is just Z generated by A minus B. So that's not the so that's the kernel of this alpha, I mean. Therefore, the image of delta has also got to be this Z times A minus B, and the kernel of delta is 0, right? Because the kernel of delta has got to be the image of this map here, and that's just coming from a 0, so it's got to be 0, and therefore we find that delta gives H1 S1 being isomorphically to group generated by A minus B. So that proves that H1S1 is has the description that we claimed. We did actually prove earlier by an argument with kind of winding numbers, complex exponentials, and so on. We already proved that H1S1 is like that, or at least outlined a proof. Now we've given a real proof using the using the Meyerowitz Taurus sequence, which we haven't yet developed properly, but modulo that, this gives you a calculation of the homology of S1. Actually, on the previous screen, I wasn't quite finished. I should have said the following. So we on the previous screen, we gave an argument for what H1S1 looks like, but we should also consider what HNS1 looks like for n bigger than 1. So we got so we have Hn of U plus Hnv going to Hn S1, and then we have a delta going to Hn minus 1 of U intersect V. Okay. And now n's bigger than 1, so n minus 1 is greater than or equal to 1, and U intersect V was just 2 points, so this U intersect V only has an H0. This one will just be 0, and similarly here, n's bigger than 1, U and V are both contractible, so that's 0 as well. And so so exactness forces that Hn of S1 0. Okay, so that really does complete the argument for S1. Okay, so now we're going to prove the claim for n bigger than 1 by induction. Okay, so okay, so let's suppose we've proved the claim about the homology of Sn for a particular value of n, and now we want to look at Sn plus 1. So Sn plus 1, so that's the sphere in Rn plus 2. I'm going to choose to write it like this. The set of pairs y, z in I want to sort of separate out the last coordinate here. So r to the n plus 2, I'm going to think of as r to the n plus 1 cross r. So an element of that is like y comma z, where y is a vector and r to n plus 1, z is just a number. And square norm of y plus z squared has got to be equal to 1. So we're going to sort of split this, just as we did with S1, we're going to split this into open subsets U and V. So we're going to put U is set of y, z in Sn plus 1, such that z is strictly less than 1. Okay, so there's only one point where if z is equal to 1, then that forces y to be 0. That's just the you just get kind of the north pole 0, 1. And so similarly, V is what we get by removing. So that's what we get by removing the north pole, and this says V is what we get by removing the south pole. And so U intersect V is the set of y, z in S to the n plus 1, minus 1 less than z less than plus 1. And if you think about it, that can be written as the set of pairs. Say x times root 1 minus z squared z, for which x is in Sn and z is in minus 1, 1. And so that's homeomorphic to Sn cross minus 1, 1. And so homotopy equivalent to Sn. Think about the case n equals 2, then here you've got the case n equals 1, so Sn plus 1 is S2. So here then S2 is like your ordinary sphere. Your U is everything, you've removed the north pole, V you removed the south pole, U intersect V is you've removed both poles, and that you can just contract down to the equator, which is an S1. Okay, so U intersect V is homotopy equivalent to Sn, whereas the these U and these V, these are both space. Let's write it here. These are both contractible by stereographic projection. Okay, so this we had some formulae for this earlier. That you take a sphere and remove a single point, and what's left is homeomorphic to Rn plus 1 in this case. It's homeomorphic to Rn plus 1 and therefore is contractible. Kind of maybe the most familiar case, S2 is the Riemann sphere, the complex plane with infinity added in. You remove, or equivalently, you remove a point from S2, what you get is the complex plane again. But it works for all n. There's a formulae for that in the notes. Okay, so the U and V are both contractible, so we certainly understand their homology. U intersect V is homotopy equivalent to Sn, so it has the same homology as Sn, and so by our induction hypothesis, we understand the homology of U intersect V, and we can just use the Meyer-Taurus sequence to work, because of course the union of U and V is the whole sphere, so we can use the Meyer-Taurus sequence to calculate the homology of Sn plus 1. Okay, so where are we now? We've got Sn plus 1 is U union V with U and V contractible, and U intersect V homotopy equivalent to Sn. Okay. And of course, so here we're assuming n is going to be at least 1, and therefore Sn is connected. So we have a truncated Meyer-Taurus sequence. Okay. Now in this truncated sequence, of course, we've lost all the H zeros. So HNU is HNV is 0. Sorry, HKU is HKV is 0. Because it's we're looking at the truncated sequence, we're only looking at the groups where K is strictly positive, and in those cases, your HKU and HKV are just 0. So what we get is like a 0 going to HK of Sn plus 1. That's your HKU and U union V. And then this goes by a delta to HK minus 1 of U intersect V. And then the next term there is going to be 0 again. The next term there is 1. Next term there depends just on the homology of U and V, and in the range we're looking at, those are 0. So delta is iso on HK. If that's at least going to be valid, provided that with this K is at least 2. Okay, because we want And so we got we conclude that in particular our taking we can take our k to be n plus 1 to get hn plus 1 Sn plus 1 isomorphic to Hn Sn, which is Z. And for other k, we've got other k at least 2. We've still got that this that's an isomorphism. So you're going to get that Hk of Sn plus 1 is 0. Okay, and then what about k equals 1? So also, you've got your H1 U plus H1V to H1 of your Sn plus 1, and then your then you've got because we've truncated the Majorvic-Taurus sequence, we just got a 0 in the next slot. Because truncating, so it's there, and then this group here is 0. We get so from that we conclude that the H1 of Sn plus 1 is also 0, and Sn plus 1 is path connected. Therefore, H0 of Sn plus 1 is just Rz. Okay. So that completes our induction step, and that gives us the homology of all spheres. So I'm just going to finish by recording a small addition to that. So let's just recall the inclusion. Let's call it I from Sn to Rn plus 1 with 0 removed is a homotopy equivalence. Okay, so we've got a map in the opposite direction that just normalizes vectors divided by the norm, so R composed with I is equal to the identity. I composed with R we explained earlier is homotopic to the identity. Anyway, the conclusion is that I lower star from the homology of Sn to the homology of Rn plus 1 with 0 removed is an isomorphism. So at least for n at least 1, we've got the hk of Rn plus 1 with 0 removed is Z for k is 0 or k is n, and 0 otherwise. Okay, so we know the homology of spheres and the homology of punctured Euclidean spaces. And in the next video, we'll have some application of that to various kind of problems in topology.